Hi, my name is Hiromichi of I'm going to talk about Parallel Universe. And during the presentation, if you have questions or comment, just go ahead and stop me. Whenever. But I will have a Q&A at the end as well. Okay. So Parallel Universe is basically a fast parallel MySQL server. I don't know if you've seen it or used it. So I'm envisioning maybe it could be used in database servers or data warehouse servers or data analytics service application. I believe Parallel Universe is the only SQL server out there with a Parallel query engine. Now it's based on MySQL server, so probably I don't know 90% of the code is same as MySQL. It's MySQL version 5.5. It's based on. Okay, it's I've taken the code from the Pakona service 5.5. So all the details are explained in the documentation website. Now, let's see. So since it's based on MySQL server, it's fully compatible. So you could use your existing queries or existing databases without doing any change to it. It's a new technology. My initial motivation was to use the extra cores that's available in your CPU, because if you look at most of the software today, is really based on legacy software. So everything was written as if there was only a single core, so a single CPU there for a single thread. So the fact that you have a multi-core doesn't really help you with your particular software because it's a legacy software. It doesn't really take advantage of multiple CPU cores. And of course, there are many phases to a query execution, and this new technology speeds up only the execution phase of it, because there's another part that's called optimizations. When you get a query, you have to figure out how to optimize it so that you know how to do it most efficiently or fastest. So this would leave the optimizer alone. You just take the execution plan that the optimizer gives you and speed up the execution phase only. So that's why the codes that involved in this technology is pretty small. Probably, like I say, 1% is different. Even though if you do the diff on the files, you're going to find about, I think like 40 files have been modified. But most of the modifications are pretty simple modification. It's because this touches the very core of a server, that it deals with how to do a select, how to do a access records, field, and all that. So that's why it has to change a lot of the files. But like I say, most changes are pretty insignificant. Okay. So like I say, it's basically MySQL server plus fast parallel query engine. And that portion, like I say, it's probably only 1% of the total. It's pretty small. So that's that. Okay, so before I can talk about how new technology works, like I said, I'll talk about how the query is executed by your server. So you take a typical SQL query, so select which fields you want to see from which tables, and then you do a conditions. So that because the condition specifies relationships between the fields from these tables. Okay. So people should know that. That's straightforward. And this is how it's done currently. Current technology takes query, it feeds into parse and optimize output. And what you end up is what you query execution plan. Okay, this tells you, okay, in which order you're going to join tables. Then how you access tables, table access method. Then for each record, they specify conditions that record has to match. Then for the output stage is how to process the record, for example. So query goes into parser, you produce the query execution plan, then it goes to execution phase, you execute, then whatever the output is basically a combination of records from each table. And that gets either sent to client or maybe written to table or whatever. Now, if you look at this flow of execution, it's all done by a single thread. Namely, it's a client thread. So each time you connect to server, you have a client thread, which is responsible for executing your query. So only one thread does all this. You got first, then you execute and do all this. Okay. So now this is a new technology. So I left out the optimized phase because that portion has been modified. So I use existing optimizer. Now the only difference is the execution phase. Before you had one single thread executing that execution plan. Now you have a multiple threads executing. Okay. And the process record method is still executed by single thread, which happens to be thread that's responsible for processing the last table. Okay. So you could have n threads possibly working on n tables concurrently. Okay. This is an example I gave you on current technology using 3 tables. So I'm not sure. Most people are familiar with how the query is executed by the server. I mean, obviously, some of this stuff may be pretty obvious to you, but maybe straightforward. Anyway, what happens in the current technology? Let's say you have a table T1, T2, T3, let's say it's joined in that order. Then what's going to happen is it will read record from table 1 to determine if that matches the conditions that it has to satisfy. If it does, then you move on to second table. Okay. Then you read the record from that table and see if that matches condition associated with this table. If it doesn't match, it will keep reading. But as soon as it finds it, it will move down to the next table. So this is what's called the recursive descent algorithm. It's basically depth first search. So basically you're searching for a combination of records that satisfy your conditions, the overall condition. But optimizer broke down those conditions for you and made a sub-condition for each table. So that's what's. So what happens? It goes to the first table. As soon as you find a match with a record, it moves on to the second table. As soon as you find the match, then it goes to the next table and so on. If it doesn't find any here on the third table, it goes back up to the next table. If it finds it, it goes down. So it does basically this kind of thing. Single thread still. Okay. All right, so this is a graphical representation. So you got table 1, 2, 3, the 3 tables of the query, and that table is processed by thread 1. Okay, the table 2 is also processed by thread number 1, and so on and so on. So what happens is, like I just explained it, it reads the record from table 1. If there's a match, we move on to the next table. It's here. The match, move on to the next one, and so on. If there's no match here, then you backtrack back to table 2. You keep reading it. As soon as you find a match, you move down. So it does basically this kind of thing. All done by one thread. So basically table takes turns in being processed by single thread. Now this is new technology. So if you notice, the only difference is that there's a separate thread associated with each table. So the table 1, the thread 1, table 2, thread 2, table 3, thread 3. Okay. Now, what happens here is that these are happening in parallel, so it's concurrent. So what happens here is that if this record here from table 1, if it's a match, it will just push into what I call inter-table buffer. Okay? Then it will keep reading the next table. Soon as you find a match, you just shove that record into the buffer. Okay? But it doesn't stop, it just keeps reading. Now, over here, table 2, thread 2, what it does is it reads the record that's sent by thread 1, because it might use this record as an index to access table 2. So anyway, it will take that record and read table 2. And if that record matches the condition, it will shove that record along with the record you just received for thread 1 into its own intertable what I call buffer, okay, which is used to feed into the next thread. So I don't know if you see what's going on here. So this one just table 1's only. As soon as you find a match, it will shove that into the buffer. And over here, it reads the record from table 1, and it reads the record from table 2. So if you find a match, it will take record from table 2 and table 1 out to next stage. And over here, what happens, it receives the record set basically from table 1, table 2, which all beta satisfy the condition both stages. Then it reads record from table 3. If it matches the condition, then that's basically the combination of record that satisfies overall condition. So that's get output. So what happens? So this is working. That's working. This is working all in parallel. There's no going back and forth. That's how it works. So there's a between the stages there's a buffer. It's really implemented as a ping-pong buffer. I don't know if you know ping-pong buffer. Ping-pong buffer is basically two banks of buffers. While one bank is written by one side, the other bank is free to be read by the reader. So when they're both done, you can just swap. You follow me? That way, it can keep writing, and reader can keep reading. And when both done, they swaps. Then, let's say, bank 1 was being written before, now bank 1 is going to be being read by thread 2, and bank 2 will be written by thread 1 and so on.
So the idea is to try to reduce how much locking conversation you're having between the buffers. Why would you implement that?
Okay, if you have a single buffer, what's going to happen is you have to know where the head is, and you have to know where the tail is. Since they are being accessed by two threads, it causes all sorts of problems. So like you may have to have a mutex or lock or something, because you cannot change right and without knowing the reading. But anyway, it's so much easier if it's two independent banks, and one is write only, one is read only. When they're both done, you swap. There's no handshaking, basically. That's why it's called ping-pong buffer. That's a term that's at least used in hardware anyway. I don't know if they use it in software. Ping-pong. Ping-pong.
Ping-pong.
So I tried it using single buffer, but then it's too much handshaking. As soon as you have handshaking, it slows things down. With that, only one handshaking, that's when you switch banks. But then these banks are pretty big, so then you can go. And when one side is done, then you have to wait for the switch. The same thing over here. So Basically, this will allow you to operate independently in something. So that's how it's important.
How much more RAM, say the standard 94 server, would this require?
Basically, not much, because I've used this inter-table buffer size to be same as the thing called the join cache. I don't know if you're familiar with MySQL server has a thing called join cache. It's used when you do a table scan. That's buffer size is 16K by default, and I use that, and it seems to be okay. So it's fine.
And these mostly select, so you're talking about only updates and inserts, it's
Just select, yeah.
selects.
Right. So if you do create table select, this is will still work. Okay. So let's say if you do select, the result goes to table, and this will still be okay. It will work. Even what's the other one? Create table, insert, what's the other one?
Update.
Update. There another name for that, right? Insert and replace. Sorry, replace. Okay, insert, replace. That will still work in this configuration. So you could insert into table, do parallel select, and then it's okay. Let me test it. Okay, so this is what's happening at each thread. So you have a record set that comes from previous stage. Then what it does is, because your table access may be depending on this record, and you take that record set, you do the access. If it doesn't match, then you shut that record set into the buffer. So you just keep doing this. You read one set, then read however many times this record is available. Once that's done, you pull a next record set. And you however many reads it's available. If there's a match, you stay. Okay. So this all concurrent. It's based on MySQL, so therefore it's compatible. So there is existing database with all this. So now, the only thing you have to do is I've created the user-defined variable called parallel table list. It's basically a string variable. So you said, okay, my database at T1, comma, my database at T2, my database at T3. These are tables that I want to be processed in parallel. So you just specify that. And that's all you have to do. The default is no string, so it's obviously processing it the same. And that's it. If it's not in there, in the list, then that won't get processed in parallel. I have some benchmarks. Now, these benchmark is based on warm cache, so it means it's a second and subsequent runs of the call. So what it does is then your table data gets stored somewhere in the cache somehow. Okay. Now, if you don't like this requirement, I was thinking what you could do is you start the server, then you can warm up in your cache by doing some dump queries. Just run some queries that access tables. That way, the records from tables gets to be stored in your cache somewhere. So anyway, here is the benchmarks. I use buffer pool to 16 gig. This is based on 24 gigs. So somebody told me I need to put 2/3 of memory to do something. Now this table, I don't know if you see, it's taken from MySQL benchmarks. You see this table, so this is the same table. And in that benchmarks, you use 10,000 records I bumped up to 1 million records. And so I guess go to 999,000, go the other way, and so on. Okay. Now, okay. Unfortunately, we got this working with it. But anyway, for the 8 tables, T1 through T8, T1 has no key. T2, I give a key of IDN. T3, I give a key of reverse IDN. And so on, IDN, reverse IDN. And then I do a 4-table query. You say, okay, give me count of from T1, T2, T3, T4, where T1 IDN equal T2 IDN, and T2 reverse IDN equal T3 reverse IDN, and T3 IDN equal T4 IDN, and T4 IDN that group is greater than 0. Now, the idea, the way I want to make my benchmark somewhat realistic, so I think most people design their schema such that you're going to have something like this. Let's say first table may be scan, table scan, resolve, but then whatever E reads, E use the field from first table to access the record from second table. So that's why I say T1 the IDN equal T2 the IDN. See? So first time is all, second time reference access the IDN. Then, so if you notice the way I did it, then T3 would use a reverse IDN, so on and so forth. So this way, your query would execute in somewhat reasonable time. But anyway, these are benchmarks result I got. This is non-power, 7.2 seconds, 7.2, and power of 3.8. Of course, the result you get maybe obviously different. Okay, now this is a table, basically similar idea. So first table get scanned, and the rest is your reference access. Then I get these numbers, 18, 6.9, and so on. It's pretty fast. So, I mean, of course, this is provided that your cache is warmed up. Okay. So if you have a I/O bottleneck service with a cold cache, obviously you won't get this kind of performance. Which one? This one?
Yeah.
This one, yeah, I believe, okay, this is a table join. And I believe I used the eight threads. Basically, each table gets its own thread. 12?
12. Yeah, because you're using 2x6 code.
2 by 6 what?
You're using a Xeon.
Oh, yeah, 12.
Export.
Well, but I don't need it. That's
Right.
I don't know how to use the other 4. You follow me? Even though you have 12 cores, I have no use for the 12 cores. It's like, that's almost like a similar situation as what you have now. You have, let's say, 6 core, 12 core, whatever, but most of the time you're using only single core in your execution. But I don't know if there's a thing called performance monitor or meter in Linux. If you look at it, and when you execute query, you go CPU, the one CPU goes up to 100%, the rest are all zeros, then it comes down. But when you use this, you can actually see that the 4 CPU goes up to not quite 100%, but 70%, 80%. So instead you have one curve goes up to 100%, down, kind of long, about 18 seconds. Now you have 4 lines goes up to about 60 or 70%, it comes down in about, let's say, half the time. So you see actually multiple threads that do the work at the same time. So that's a pretty good graphical representation of that. So, okay, this is my item. I found my item, I get a lot more better performance. I assume that's because there's not much less bookkeeping with my item.
Yeah, it's not transactional.
Right, so it doesn't have to
The beauty
commit.
is- Well, actually, that comes to the question is your engine as compliant or not, as far as preventing corruption and
Yeah,
is it
this,
supposed to be my ISM or supposed to be NVD? It should be
it,
data.
I didn't do anything to break ACID compliance
Okay.
with this database server. So whatever that worked before should work now with this. Okay. In other words, it just does speed up your query. It does not do anything else. I did not remove any commit or checking or any of that stuff. So it should work. All the transactions should still work. But obviously, you don't get as dramatic performance improvement as my eyes. So here, the 3-to-1. This is 4 tables. And this is 8 tables. Now here I'm doing a 5x speed. And I also did 16 tables. Just
Because face it, we've seen these queries.
Yeah.
just because I can. I had these are numbers I got 6, so it's about 6 times less. I guess if you do a lot of data analytics type of work, you could have quite a few number of tables. So if a company like a NetEase does things in, let's say, 4 hours, which would normally take 4 days, kind of thing. Now they'll deal with stuff like, I don't know, 20 tables. I don't know. I'm not too familiar with NetEase, but their hardware solution, some of them is millions of dollars. It's a very expensive issue. So here, what you could do is you can just take your old x86 type of things and get somewhat close to reasonable performance. Let's see. So that's about it. So, does anybody have any questions? Has anybody used it? No used it. If you go to the website, there's white papers in technology and more benchmarks result, because these are the 8 tables, 4 tables, 16 tables, with a million records per table. There's a benchmarks with the small tables, with 10,000 records there as well, at the website. So I don't know what kind of table size do people work with. Is it pretty big? Million records? Less? So okay, that's okay. So yeah.
Working with multiple tables, is there any advantage to putting the ones with more records, like number 1, or number 2, or number 3,
You don't have the choice because that table join order is determined by the optimizer. So whatever optimizer decides table 1, that's what it is. You don't have control over it.
You can't control.
No, I don't have control over it. Because I just take what the optimizer gives me and just speed up the execution phase of it. So there's a lot of work going into optimizations. I don't think I can do much better job than that's been done already. So in a nutshell, this is what the Parallel Universe does. Any more questions? Yep.
I assume this is something that you can install pretty easily.
Yeah. Let's see. if you go to website, there's there's a source code as well as binary available in like a 32-bit version, 64-bit version, and one for Red Hat, Fedora, CentOS versus SUSE, OpenSUSE, and also you can get that from Amazon. It's listed under community images. There's a lot of images that's contributed by the community, people can use. So you can get that from Amazon. Also, there's a company called GoGrid.com. That's about it. From these Amazon and GoGrid's all binaries, but you can get the source code from their website. So 32-bit, 64-bit. It's pretty straightforward. The user's guide have download instructions and pretty much download the TOR file onto under there. You can use your existing data directory, and you can even run this Parallel Universe in conjunction with your own server. Just give a different port number and so on and so forth. But because you need to have two different data directories, so conflict. So guess that's about it. And there's a users forum and stuff. So if you have a question, also the email, support email. It's all the stuff is at the website. You can take a look. Any more questions? Yeah. What do you mean? How do you
Performance-wise.
I don't know. I noticed a similar configuration. Intel chip seems to do a better job. I don't know why. Maybe it's got a better caching mechanism inside. Yeah. I noticed.
And they'll have a larger cache and a slightly slower speed.
Yeah. I don't want to be too partial, but Intel seems to be does a little bit better. But it's hard to really say. But I use Intel's 4-core processor and also AMD 4-core, and so I suppose maybe they're better Intel. And yeah, those are two processors to use. I don't think there's anything else you can test with. But I've tested on Fedora, CentOS, Red Hat, SUSE, what else? Ubuntu, right? So pretty much most Linux distributions that you can think about, I've tested it, so it should be good to go. And, yeah? Oh yeah. Oh, I didn't test against operating systems, but my guess is that there won't be too much of a difference between, let's say, Fedora versus CentOS, SUSE, because the underlying Linux kernels are the same. So I'll be surprised if you find a big difference amongst different Linux distributions. I didn't really look for it either, so I mean, there may be some difference in performance. I know there's a thing called AIO, sequence IOs. Some support, some don't support, but I don't think it matters here too much. So, I mean, have you seen any difference in distributions, Linux distributions, performance-wise? Right. Yeah. For this one, I also have a G libc 2.5 version also, because some people are still using old Linux, which based on G libc 2.5, so that's also available there, as well as 32-bit, 64-bit. So, any other questions? Okay, thank you for coming.